Okay, so picking up part 2 of homework 8-3 here, we've got just questions 8 and 9 to wrap up. And neither of these questions I don't think are terribly difficult. There are a couple little tricks along the way though to make sure you're paying attention. So question 8 here, it looks like a pretty complicated situation at first, but they're just asking us for the time that it takes to complete one cycle, right? One complete cycle. So in this case, the ball is going to swing down, it hits the spring, compresses the spring, returns back to that equilibrium position, and then oscillates back up. So the easiest way to approach this is I went ahead and just found the period for both this spring and the pendulum system, right? So the period for the pendulum system would be about, if I plug in the length of the pendulum and the acceleration of gravity, would be about 6.28 seconds. So that would be the length as if the pendulum was just swinging back and forth unabated, right, without any restriction. Okay. The period for the spring, if this spring was just oscillating back and forth, would be 2 pi times the square root of m over k, so about 0.672 seconds once I plug those measurements in. Right, so again, I found the total period for the pendulum, and then I found the total period for the spring. But the trick to this question is we don't actually use the full period for either one of these motions, right? If I think about this, the pendulum swings down, it goes a quarter of the period, compresses the spring, which goes from equilibrium to 1 amplitude and then back to equilibrium, and then the pendulum goes back another quarter of the period, right? So if I think in terms of the pendulum's motion, the pendulum is only executing half of its motion. It's swinging down to equilibrium, and then eventually it's swinging back up to that amplitude. So if it's only executing half of its total motion, then it's only going to take half of the total period worth of time, right? So it's only going to take half of that period. So the 6.28, I'm actually going to end up dividing that by 2. The same thing is true with the spring. The spring goes from, when the ball hits it, it's at its equilibrium position. So it goes from equilibrium to an amplitude and then back to equilibrium before it releases. So that's only half of the spring's period as well. From equilibrium back to equilibrium is only half of the motion, right? In order to be the full motion, it would have to go from equilibrium to amplitude, back to equilibrium, to the other amplitude, and then back to equilibrium. Okay, so each of these motions only undergoes half of their period. So what I did was I just found the total time as the total of their 2 periods divided by 2. So I added up the 2 periods divided by 2, and it should end up being about 3.5 seconds. So about 3.48 seconds, obviously depending a little bit here on where you've rounded the answers off at. But again, you should end up at about 3.5 seconds for the period of this whole kind of obscure motion here, right? So anyway, something to make sure you're comfortable with on that question. And then question 9, I hope was not too bad. It really isn't anything too crazy. There are several parts, but I think each part individually is not too bad. So for part A, they ask us to find the period. Well, to find the period, all I did was I took the interior function of that function that they gave us, right? So I took the 2.74 radians per second, and I simply set that equal to 2 pi over the period, right? That's one of the options I have for the interior of that function, and I just set that equal to the period and then solve for the period. So we get about 2.29 seconds for our period. Once we have the period, finding the maximum velocity is pretty easy, because if I take advantage of the equation we've seen before where we do 2 pi times the amplitude divided by the period here, the amplitude is the 6.2 centimeters, so notice I converted that to meters, right? And then the period I just found to be 2.29 seconds, so I've got 0.170 meters per second. Now again, this is certainly not the only way that you can find this maximum velocity. You could also have done the derivative of this function, and it should give you pretty much that same answer. But this is probably the easiest way to do that. Same type of thing is true with the maximum acceleration. You could have actually done the second derivative of the function, but the easier route by far would be if you just realized that the maximum acceleration equals the amplitude times the angular frequency, right? The angular velocity of the angular frequency. So my amplitude once again was 0.062 meters because it was 6.2 centimeters. And my angular frequency, I'm just using this interior of the function as being omega times t, so that 2.74 is my omega. So that's why I plugged that number in, 2.74 squared for my omegas, because that's what that represents. So then my maximum acceleration is 0.465 meters per second squared. As soon as I find those measurements, finding d and e is pretty easy, right? So for part B gives me the maximum velocity, So to find the maximum kinetic energy, I just need to take my mass, which they told me the force of gravity is 44.1, so my mass would be 44.1 divided by 9.8, which is about 4.5 kilograms, and then times my maximum velocity, so 0.170 squared, and that gives me 0.065 joules of energy. And then for part E, they asked me to find the spring constant, so I took advantage of my period equation. 2.29 equals 2 pi times the square root of m over k. Again, I know my period. I found my mass by using the 44.1 divided by 9.8, and I solved for my spring constant. So anyway, that wraps up then the second part of homework 8-3 here, and then hopefully you guys don't have any questions on this stuff, but if you do, by all means let me know. I'm definitely happy to help you guys out with this, but I think probably the last page or so here wasn't too bad for most of us. So anyway, if you do have any further questions, just let me know.